let's try to understand intuitively what are the different cases that we might find when we are looking for bounding, and getting a finite interval within which the optimal solution has to lie. Okay. So when we are doing in the bounding phase, we will essentially get into various cases. Okay. For example, what I am trying to depict here in this plot, that we have x and we have fx, and let's say this is the general nature of the function that we are trying to optimize. We know that the optima here just by looking at the figure, but the algorithm doesn't know, but we have to help the algorithm find the location of that. So the first step of that location would be something like this, where we want to say that, okay, rather than searching the whole space from here to x right here, what we need to do is maybe we can make the job of the algorithm easy by saying that, okay, you know what, I know for sure that the solution lies between these two bounds. Okay, why don't you search just within these two bounds itself? And that is essentially the bounding phase. And so the first step we'll do is write an algorithm that will help us in bounding and saying the smaller region interval where the optimal solution lies. Okay, so if we are into this bounding phase, right, here is some key intuition that we need to develop before we develop the actual bounding algorithm. So let's say if I pick 3 points on this function, okay, and if I project them to the x-axis, right, this here, and this here, and let's look at the middle point, which is denoted by x0. And what we have done is intentionally we have moved by delta distance to the left of x, and that is x0 minus delta, which is right here. And then we have selected a point which is like delta on the positive side of it, right? So this point, essentially the point that is located here is essentially x plus delta, x0 plus delta. Okay, so now we have selected on x-axis x0, x0 plus delta, and x0 minus delta, which are these 3 locations. This point, this location right here, okay, this location right here, and then this location right here. Okay, and then we have basically sampled the function on those locations, right? So we have sampled those functions, which are these 3 red dots that you see on the function plot, right? So let's call these 3 points the x1. Let's call this one the point like this, the x0 minus delta, as x1, and let's call the x0 point is x2, and let's call this x0 plus delta point as x3. So essentially what we have done is we have found these points x1, x2, and x3, and there is a relationship between them. X2 is the middle point between x1 and x3. And then at those values we have sampled the function, and we have got the function values of fx3, fx2, and fx1. Okay, and this is essentially what we can do is once we have this x1, we can pass on that value to the function value, and we can sample that function, and that's what we are going to do here. Now once the sampling is done, then you will see that we will lie essentially in 3 main cases, and depending upon different cases we can do different things, and we can guide the algorithm to find an interval bound, and that's what we are going to be focusing on. So let's see what those cases are. So you will have these 3 samples on the curve, and you will see that typically in this case the fx1 is greater than equal to fx2, which is greater than equal to fx3, right? If that is the case, we know, which is basically what is shown here, then we know that optima probably lies on the right hand side. So what we should be doing, we should be sampling and moving away, and we should be sampling this somewhere on this location of the function, okay? Or when we project, essentially we will be moving on the right hand side, right? So we should be moving to the rightward if this is the case that we fall in, where your fx1 is greater than fx2 is greater than fx3, which is the scenario depicted by these 3 sample plots that is out there. So in this case, we will move right, and then we will begin the algorithm with this point, and this point, and check for the condition, and we will decide which direction to move. So that is the case 1, but you might also fall into other cases, and we need to account for all the possibilities that are there before we arrive at the final algorithm that will help us in bounding the overall interval in which the optimum solution lies. Okay. So there might be another case where you now have these 3 points, right? x1, x2, and right. And in this setting, what is happening, you can see that the fx3 value is greater than fx2 value, and it is greater than fx1 value. So in this scenario, what is going to happen is your optimum solution is probably going to lie on the left. So what we should be doing is, if the function is going like this, we should be sampling the function somewhere like this, right? So in this case, moving to left is the right idea. So when we have this scenario where fx3 is greater than fx2, which is greater than fx1 for the 3 consecutive points that are sampled on the function itself, then we should move left, because we know that the optima is going to lie on the left, and because this is the smallest point, so we should keep moving in this direction. So this direction, the function is decreasing, so we should be moving in this direction, so the move should be directed leftward. So that's the case 2, which is okay, left move case, right? And then finally we have the third case, where we might have 3 plots like this, where the fx1 is greater than fx2, and then fx3 is also greater than fx2. So the fx2, right, the x2 lies between x1 and x3, and this function value of function where the x2 has been sampled, the function sampled at x2 is lower than x1 and x3 together. In that case, we know for sure that these two are good interval to bound the algorithm, and this might, in between these 2 points, x1 and x2, we have an optimal lie, and probably we should stop here, and these 2 points, x1 and x3 themselves, could be the bounding point, or the bounding, they can define the interval, right? So in this case, what will typically happen, then we will project this point and this x1, x3 point on the x-axis, right? So if once we project this on the x-axis, right, this will become the x upper and this will become the x lower bound of the overall problem. And this, we will spit out this x1 value, and we will spit out this x3 value, and this x1 and x3 gives me the bound where the optimum lies, right? So that's what we will do. So we will basically finally output that x1 and x3 is the bound where we should be looking for the optimal solution, right? So that's the bound that we are looking for. Okay. So this is the 3 different cases. So what happens is, like, typically you start the algorithm randomly at a certain point, and you look for which of the 3 cases you are falling into, and based upon those 3 cases you decide whether to move right, left, or to exit, which will be in the case 3. Okay, and we will go through an example problem to understand these cases in more details. But with this intuitive understanding of 3 different cases, let's go and chalk out the main components of the bounding algorithm, which is the Swan's algorithm that is out there.